And I think we could start. Welcome back, everyone. So we just got through our very first exam. Congratulations. We have two more to go and then the final exam. We've looked through that schedule. Our next one is going to be March 12th. And we're going to repeat everything we do on the Moodle website pretty much verbatim. What I mean about that is when we get around this week, you're going to start seeing more and more information pop up, the exact coverage. You'll see review problems, things of that nature. And it's just a redo of everything else we did above here, leading up to our first exam. So our second exam's down there, and I intend to have our first exam graded either Friday or potentially Saturday on this weekend. Hopefully not the weekend, but if it takes it to that, we'll make sure it happens then. Once these exams are graded, I'll post your grades to Moodle right away. You can check your grades right here. And just so that you don't have to feel the need to log in like 50 times over the weekend, I'm also going to email everyone the moment the grades are put in, so you'll know when they're actually.
Yeah, I had to sign into my Zoom class.
Sorry, say again. Might have been open mic. Let's put that there. So that's our exam one. After we take a couple questions to start out the class, we're going to go into plotting sine and cosine functions. But other questions at the moment, folks, before we get started? There aren't retakes in this class, unfortunately, but I do have an extra credit opportunity related to exams once we get closer and closer to the end of the semester. So although there aren't retakes, I'd let the final exam count as an extra credit opportunity. And we'll write this down in a very specific way so we know exactly what I'm talking about. But the way the extra credit works with relation to exams is if your final exam score is higher than your minimum score among exams 1, 2, and 3, your final exam score will replace it. So if you have one exam that you felt like it was a kind of an off day for you, you can make that up absolutely with the final exam. Alex says, what was wanted in 23-28? No worries, we'll take a look at that one as well when we get to that question, Alex. Other questions at the moment, folks, about either the exam or otherwise? Okay, and I should also mention, one thing that I haven't said specifically yet, but I'm intending to make an announcement up here for all my classes, is that the due dates that you see here, I'm not going to be I actually take them off after they go past due. Let's see, let's go to one that still has a due date. That would be this one. After it goes past due, I take the due date off of it. It's just gone. And here's what the due dates are really going to be in this class. I did say something different in the syllabus, but this is how it's going to work in practice. The due dates are more for the sake of pacing of the course. If your assignment does go beyond the due date, maybe you had a question about it in class or something like that, I will accept it for full credit if you get into me at some point. I mean, before the end of the semester, of course, then I'll accept it for credit. So think of all these as, this is a benchmark. If you have it done by that date, you're considered fully caught up. If you need to take an additional time, please do so. I mean, the objective of the course is to learn this material. If we have a rough patch in life or anything like that, I'm not opposed to people taking additional time to get these completed. So thanks for asking about that question there as well, Alex. Other questions or comments at the moment, folks? Okay, I want to go to this question next. Again, this one was asked quite a lot in class, or not in class. This one was asked quite a lot over emails and such. I think about at least 40% of the class asked about this one. It's a tough one to even start, so let's begin there. I'm going to save the notes that we do on this one and put it right here in 5.4. So we're extending that section out just a little bit. That way, if you want to go back to those, you can find them in the 5.4 document. Just seems like the sensible place to put it. So in 5.4, we did a number of things. We dealt with SOHCAHTOA. It's not too bad to draw that diagram. That was a problem in the homework. This one right here is kind of like what we were dealing with in that homework problem that we're working on. All we know is tangent and angle and one side, nothing else. These are pretty hard to get through. I indicated to a lot of people Pythagorean theorem is a way to start, but there are multiple ways to do these kinds of problems. Let's go down below and solve this one. Let's go down way, way below. And here's where we'll solve this one right here. So to get started on this thing, definitely you want to draw out a diagram. This is going to relate all that information in a sensible way. So here's our right triangle. If we call this angle A, then side A over here on the opposite end would be of 20 units, whatever the unit is. They gave us B, so here's a side B and a side C. And I forget the instructions, let me double check. Find the lengths of the missing sides. Okay, so we want to know what is the side B and what is the side C. And what makes this a challenging problem is there are a lot of ways to start it. Some people might have found that the angle B, it just has to be pi over 6 or 30 degrees because sine at pi over 6 is 1/2. If you put 30 degrees here, you can work through this pretty fast. So let's put that down as a hint. It won't be the way I solve it since I think it's a fun way to try it on your own to see how it goes. But here's a slick way to solve this problem. Use sine B equals 1/2, implying B is 30 degrees or pi over 6 if you prefer. So that's a great way to start this question here. The next thing we can do is, well, aside if you're not going to use that hint, you can just use this directly and write out that sine squared of B plus cosine squared of B must be exactly 1. This is going to allow us to solve for cosine of B. And once you've solved for cosine B, we can actually crack open this diagram a little bit better. So let's run through this right here just to show that next step. We're going to square 1/2 plus cosine squared of B equals 1. The square root of 1/2 is 1 squared for a 1, divided by 2 squared for a 4. So we can make our right-hand side now be 4/4, so that cosine of B, squared still, is 3/4. And I really thought I'd fit all that in there. Let me scroll just a bit. When we take the square root of both sides, there is a plus and minus involved, but we also know that we're dealing with the side length here. And cosine is, or let me say this a little bit better, B is an acute angle, which means we're dealing with something in quadrant 1. Cosine is just going to be positive when we take the root here. So we'll get cosine of B is the square root of 3 in the numerator, divided by the square root of 4, which resolves into a 2. So now that you have that, the question is, well, so what, right? This doesn't solve what C is or lowercase b is at all, but then you can go and do this next. Here's where the good old SOHCAHTOA finally comes into play. If you have a value for cosine B, you can now write cosine B again. It seems weird because we just found cosine B is √3/2, but through SOHCAHTOA, it's also, let's go over here, the adjacent side, divide by the hypotenuse, and I intended that to be green. Let's just slap it with a green marker. Secant. Oh yeah, they would have flipped to have C in the numerator. Yeah, I think a secant would have been a good choice as well, maybe even better. So also, if you like, try this suggestion. Try secant. You would have to flip this one, so it's 2/√3 to make it compatible. But yeah, that'd be a good process for this one as well. If you kept it as is, here's the punchline. Take that result, √3/2. You can now equate it to this result, 20/c. Next thing you do is a full-on cross product. It's always fun to do a cross product. We don't refer to those a lot in math, but that just means multiply cross equality this way, multiply C across equality this way. We have C √3 equals 40, and that means things are starting to look up and up at this stage. Divide by √3, and C is 40 √3s. You can rationalize that to do everything you'd like with it. But now that you have this value, it's just a Pythagorean theorem away to get the value B down below. But these are tricky questions in all honesty. We did one like them, but they all feel like they're their own thing each time you look at a new one. Does that help out folks with seeing how the process goes here? Sorry, say again. Oh, gotcha. So this is the kind of the longer way, but it's the straightforward way. I kind of like it. It reminds you of this identity, which is useful. So you're practicing that. You're also doing interesting things with SOHCAHTOA, equating things with algebra. But this is still a really good approach as well. If you can just find the angle B, because you note sine B is a half implies it's pi over 6 or 30 degrees, this is a really fast way to solve the problem. So if you want to take another look at it, try doing it this way, but this is just fine as well. It's got good things going for it as well if you go this approach. Well, there's another additional question. Let me pull up the chat. Alex was asking about number 24 as well on that same homework set. So let's take a look at that one. So it looks like we're dealing with figure 14 for that whole set 17 through 24. Let me double check. Oh, maybe not, wrong one. Let me keep going. This is the one we're dealing with. So let me pull this in. It's kind of hard to get exactly what you want out of that. Here's our figure 15. And back to the textbook, we're looking at problem number 24 on this one. We want to find a cosine of A. Yeah, definitely we want SOHCAHTOA here. Looks like the only thing we're missing though, even before SOHCAHTOA, we'd want to know the hypotenuse to get us started. So let's put down a C here. Hit it with Pythagorean's theorem. C squared equals A squared plus B squared. Now, A could be 8, but I would highly encourage you to think of your A as being 10 because it's opposite of this angle A. It's always good to keep your diagrams consistent in that way. So let's call this A 10, and this will be the B. Here's angle B. Then from here, we can start plugging information. This is now C squared, or like Michael mentioned the other day, you could just take the square root right here and work it through if you'd like. Take your A, square it, so that's 10 squared, or 100. Take your B and square it, so that's an 8 squared. So now we have C squared is 100 plus 64, resolving to 164. I'm not certain if that's a perfect square, but let's say C is root 164. That might simplify. I think I'm too tired at the end of the week to worry about it. Let's just write it in as root 164. And that is allowable. You don't have to work super hard on breaking down the roots, simplifying, unless you like to and think it's kind of fun. Then I'd say go for it. Next, we're pretty much all set here with a good old SOHCAHTOA. We can say cosine A is going to be the adjacent side to A. The adjacent side to A is this right here for a value of 10. Divide by the hypotenuse. So we just take this, root 164, and we're well on our way. Now this does simplify a whole lot. So if we're checking the back of the book, we would want to simplify this. But if we're confident in our answers, then I would say that's okay to leave it right there. I would give full credit to that as an answer. Oh, sorry. I said sine is the opposite over hypotenuse. Thanks for spotting that. That was my mistake on this one. If this was an exam question, I probably would have gone like this, -2 out of a 5-point problem, because that's a big feature of SOHCAHTOA. Adjacent side is that side right there, the 8. Thanks for spotting that. So an 8 should be what goes up here. I think I saw a lot of people double checking their work and noticing something wasn't quite right. But other questions with getting through that one? Okay, any other questions, folks, on that 5.4 set? Okay, well, let me take a look at, oh, I should mention, I am going to save the notes that we have here, and I'm just going to re-upload them right here, overwriting it. So all of our comments on those questions, they'll never really go away. I mean, they're also on the YouTube video, but no one wants to click through a video to find math. That's weird. Next thing we're going to get into is, well, we did our chapter 5 objective. If we wanted to define trigonometric functions, we had to define the domain. Then we defined all the functions and looked at properties. But in algebra classes, after you define a function, the almost immediate next step you're going into is graphing those functions. So that's what we're going to do right here in section 6.1. And this right here is just a cool little GIF, I think is the right word, that shows what we're getting into. There it is, folks. That's sine and cosine. Our goal is to understand just what's going on in this picture by plotting the cosine curve and the sine curve itself. Then we're going to start plotting transformations of these kinds of curves. But as we observe, if the angle moves in this positive way, well, sine is going to be the first coordinate, cosine is going to be the second coordinate, and here's how they would plot as actual graphs. There is some little confusion here, however. When we start going to graphs of a function, our graphs have this feature. There's going to be an x-axis, and there's going to be a y-axis. Having it move is a little bit weird, but that means we have to get used to cosine x equals some value. We're going to let x now be the independent variable going inside the cosine function, in other words. So that's cosine and sine dynamically changing based off the unit circle, but we're going to plot things in a more static way. So our goal, once I get a plot going, is to be able to produce these kinds of plots. Not necessarily plots like that. We want to know how to do transformations, all of these kinds of things. The periodic nature of sine and cosine means these are really great for modeling real life data like temperatures, tides, anything that has a periodic nature. So we're going to start putting in transformations, maybe a 3 pi. Notice it's changed the period here, how it repeats. We might phase shift it. We might change the midline, do all sorts of things to it. Other classes might add even more, but this is more if you're modeling like financial data at this point. Now there's a trend curve, things are going upwards. The cosine squared on this one. Yeah, pretty much what cosine squared does is it eliminates the negative end of the axis in that case. Now everything is pushed up as a non-negative function in that case. But cosine squared is pretty interesting as a transformation in its own right as well. So those are the kinds of things we're going to get into. And here's how the note starts out. Really, we need to talk about periodicity and amplitude first before we plot any of those functions, because the plot of those functions depends heavily on what is their period and what is their amplitude. And for kind of a preview of what we're getting to, we want to plot all 6 trigonometric functions. That means there is a set of notes that I will be providing on exam 2. It's not a bad one to, let me see, where did I put it? I have not put them on there yet. Should not have said that, but I'm going to put down a set of notes related to plotting all 6 trigonometric functions, and it will be included on the 6th exam. Well, this right here is really just review when we talk about transformation of functions. These are the major kind of things that we're going to be looking at. If you put here sine x minus c, we're shifting to the right. Sine x plus c, we're shifting to the left. So this is some review information about transformations of functions from college algebra, but we're going to study these things directly. This is more just a resource if you'd like to take a look at it as a preview. Well, let's get started, folks. Looking through the notation here, we'll say a function is periodic whenever you have this equation holding. A periodic function does something kind of amazing. You can take x plus some quantity p, and it can come out as just f of x. The smallest p that works above is called the period of that function, and both sine and cosine themselves are periodic. We really want to know what is the period of those. It wouldn't be period 0, it'd have to be a positive number. But if we notice, if we look at those values, they repeat after turning one full turn on the unit circle. Turns out sine and cosine have period 2 pi. That's not the same for every trigonometric function, so that's why we have to delve in deep and figure out just what each and every one of them is doing. So the period is the smallest amount that you put inside here to allow the function to repeat. Sine and cosine are the only 2 trigonometric functions that also have an amplitude. The rest have no amplitude whatsoever. To have an amplitude, your function must be bounded. Some of our functions are unbounded, and they're the ones that have undefined possibilities. All other four trigonometric functions have vertical asymptotes, making them unbounded. But sine and cosine are bounded, which means you can define the amplitude in this way. We take the maximum it takes, the minimum it takes, and divide by 2. Also, if you're just eyeballing a graph, you can visually inspect that graph and determine the amplitude just by looking at it. That could be a potential exam question right here. So it says, for each function whose graph is given, state the value of the period, try to keep that one in green, and the value of the amplitude in blue. Let's maybe do amplitude first. I think it's a little bit easier. The way we're defining amplitude is not minimum or maximum to the minimum, not peak to trough. We're thinking of the midline first. The line that this curve seems to be oscillating around looks to be -10. The distance from that midline to a peak, or the distance from the midline to the trough, is the amplitude. So from here to here is A and P. I'll often write amp as a shorthand for amplitude. Looking at this, well, that's a distance of 5, so we can say amplitude on this problem is a 5. I put the formula here just for the sake of completeness, but on the kind of problems that we're going to work it on, you can visually inspect it and just say what the amplitude is. So it's more of a concept question when we ask these ones. Any questions, folks, with the amplitude? Next one's a little bit harder on this one. I said the period of cosine and sine is 2 pi. But that's not your ordinary cosine and sine. There's have transformations applied to it. So it has a different period. Has anyone spotted what the period would be for this curve? It's kind of tricky. It's a little bit trickier than amplitude. But it's going to be the smallest value of p such that the curve repeats. If we're looking at a curve, we're looking for the smallest distance where if you just cut and paste this curve, you're generating the entire sine wave.
So is it like 5?
It wouldn't be 5 on this one. It's going to be a little bit bigger because we have to allow this
10?
and then count that distance. I
Oh,
think it might be bigger than 10 on this one. But here's how we can think about it. Let's maybe start at either a peak or a trough. If we start at a peak, because that's a natural place, I want to go this far. From here on out, if I kept plotting, I would just be repeating myself over and over again. Oh, sorry for missing a chat. Alex was saying 20, and yeah, I agree with both Alex and Higgins. This one ought to be a distance of 20. From here to here is 15, 5 more, we have a total distance of 20 altogether. But there's a lot of ways to see this. If you instead drew or allowed your finger to trace out from, say, here, we would stop right at that spot, because beyond there, the curve is just repeating itself over and over again. That means we're going from -20 to 0, distance of 20 again. You know, I think it's a little bit easier to see it from midline back to the midline again, and then that's the repeat section. Either way we see it, though, we have a period of 20.
so it's just like a full unit circle, like one period.
Exactly, that's what's going on. Absolutely. One full rotation in a certain sense. Sorry, say again. Yes, there is. We're going to look into those formulas down. They're down here somewhere, I promise. These are the formulas that are going to generate period, amplitude, and other great stuff based off of whatever your equation looks like. Absolutely. And these are the kinds of things that are going to give us the bare minimum to give an excellent plot. So we'll be focusing on these quite a lot. And I give a summary of these for all 6 trigonometric functions. That will be the handout. That's the document I thought I uploaded, but I didn't. Other questions so far, folks, with getting through this one? Okay, let me add just so the notes are slightly more readable. We found the period is 20 because that was the distance from here to here. So period is 20 for one full repeat. Maybe that's not a good idea. Let me take that line off. Well, now that we've done it for this graph, one word of warning, if this is an exam question, I usually give 3 different graphs. And we're going to say amplitude period on each one of them. You're just visually inspecting like we did here. So if your numbers are a little bit off, but they're in the right ballpark, you still get full credit for that. But watch out for this part. If you ever see an unbounded function, amplitude is undefined. It says here, assume f is bounded so that it has a maximum value m, a minimum value lowercase m, then amplitude is defined in this way. If it's unbounded, unbounded means there is no maximum or that there is no minimum, or both. There could be problems on either end. So if we look at, say, this one, that's an unbounded function. There's vertical asymptotes, and when the curve just goes up like that, and the graph is cut off, we're assuming it's just going up forever, and it really is. So on this problem, we would say amplitude is undefined. The reason is there is no maximum. It has a minimum, wherever that height is. Looks like it's maybe 1 potentially, if we're eyeballing this really, really carefully. But amplitude is not a concept for this problem, only because it's going up forever on this graph. If it actually did have a bound, I would have to show you this part of the graph where it capped off. That's how you would know it really is a bounded function. Well, because it's unbounded, there is no amplitude, but it still has a period. Any volunteers for what the period is approximately on this one? I think it's a little hard to see.
Maybe like 8.5 or something.
It'd be about a 3. If we go from, say, this value, that's where a minimum
Sorry,
is.
I thought it was a 10, like one little
Oh,
bracket.
gotcha, no worries. Yeah, it looks like it's about 3. And you know what? I think this one is exactly pi, actually. But if you were answering this as an exam question, that's probably what I would expect most people to put down. And that's absolutely full credit. It's always understanding that if you're answering these things on a graph, it's just a visual approximation. Any questions, folks, with amplitude period on this one? Okay, well, that was so fun. Let's try it again. This one is bounded. However, it doesn't have an amplitude. It's got another weird feature about it. Notice it kind of goes down and then has a horizontal asymptote. It's just going off in this direction. Let's double check our definitions for a moment. Assuming f is periodic, in other words, if your function is not periodic to start, amplitude is undefined again on this process. It has to be both periodic and bounded for amplitude to even make sense. What's wrong with this one? Well, there's no periodicity here. Nothing appears to repeat. It looks like the curve is just doing this. There will never be another peak like we see. So we would have to say again on this one, amplitude is undefined since this is not periodic. But if you said it's not periodic, the period of this thing is also undefined. There's nothing repeating here on this curve. So we'll say P is undefined. Really, for the same reason we said right here, this is not a periodic graph at all. Periodic means things are repeating like here, or like on this one, and having an amplitude means that's what the picture should look like. A maximum and a minimum should be readily spotted. Here it's implied the curve is going up forever on these locations. But kind of weird stuff. Some of our trigonometric functions have amplitudes, some of them don't. But all of our trigonometric functions will have a period. 2 pi, maybe pi, depends on the function. Well, now we know what we're talking about when we say periodic functions. Our next goal is we need a good clean plot of both sine and cosine. And the purpose of this is really twofold. we need to know how to take our information from chapter 5 and plot this kind of function sin x. But the reason we need to see a good plot on this is we're doing transformations on that plot. We're really wanting to plot these things. And the way to get an accurate plot is you have to know what the original sine wave looks like. Then and only then can you use this information to do a really fast transformation of sine as a graph. So that's what we're going for. But first, there's one question that I forgot I put down here. That's a good question to take a look at. Let's calculate cosine 32 pi over 3. It just sounds unreasonable in a certain sense. But remember, cosine is a periodic function. If we use that period just right, these are fast problems. Here's how we're going to start. Let's analyze the angle 32 pi thirds. We would rather deal with the angle that's between 0 and 2 pi. That's where all of our information is. So let's break this down. 32 pi can be partitioned as 30 pi plus 2 pi. I want to find a value right here that's less than, well, yeah, 6 pi. Reason 6 pi is because the divisor is 3. Let's put the divisor here, 3. We now have 30 pi thirds plus 2 pi over 3. 2 pi over 3 is now the angle we want to work with. Pi over 3 would be its reference angle. And this thing is just a whole bunch of rotations. So now we're looking at 10 pi plus 2 pi over 3. If we were going to calculate that in a chapter 5 setting, we'd probably draw a unit circle. Let's do that right here. Here's the unit circle. And if we're doing 10 pi, I guess a question for the class is, how many rotations is that? Is that 10 full rotations or 5 full rotations?
5 full rotation.
Exactly, as folks are saying in class and over Zoom, thanks Hayes, that's 5 rotations altogether. So let's pause, or let's first do those rotations. Here's 2 pi, 4 pi, 6 pi, 8 pi, and finally 10 pi, 5 full rotations. Then we're not done rotating, we have to go 2 pi over 3. 2 pi over 3 is going to terminate out here. But that's the location for 2 pi over 3. It's also the location for 32 pi thirds. That means we don't have to work with 32 pi thirds. We can just use 2 pi over 3. Cosine is the x-coordinate, and that would be about 1/2. Excuse me, that's exactly 1/2. And so here's how this goes. We're really just using periodicity whenever we do this kind of stuff, but it's a chore to spin around 5 full times each and every time. Here's what periodicity would allow us to do if we're doing this purely analytically, no graph. We would write cosine 10 pi plus 2 pi over 3. Because the period of cosine is 2 pi, any multiple of that also allows it to wipe out. So if that was a 12 pi, a 16 pi, it's just gone, but not 15 pi. It cannot be odd. That's a different setting. That would take the angle and throw it down over here instead. So even amounts of pi just cancel out because the period is 2 pi. Now all you're really doing is cosine 2 pi over 3. And that converts to a negative 1/2. So this is not like the world's most fun or fancy problem at all. It's not necessarily an exam question, but the purpose of this problem is to observe that cancellation right here. This is what periodicity looks like if we're only looking from an analytical point of view, not those graphs from before. But from the unit circle point of view, that's also exactly what happened and why periodicity works for sine and cosine. Any questions, folks, with that output right here?
Do we need to, if this was on a test or like homework problem, do we need to draw everything, or we can just like cancel the 10 pi as usual?
You could do it just like that, like you see here
Okay.
on this.
For sure.
Other questions about it? Okay, Yeah, the illustration here was only just to see what in the world is happening when the 10 pi got canceled. Well, what we're going to do next is look into plotting both sine and cosine. We'll try to do really careful plots, and that's what's going to segue us into plotting the so-called, our author calls them sinusoidal functions. That's a weird word. That's just a way to say transformations of sine and cosine. So down below, this is not a question that I would ask directly on exam, but it could be a homework question, so it's worthy to do this careful. It says sketch the graph of f of x equals sine x over one period. Then we'll state period and amplitude, domain and range. But again, this is where it gets a little bit unusual. We're used to seeing sine and cosine defined here by a unit circle, but if we're going to plot it as a function, we change the input variable to x. We're plotting over an XY graph now instead. And it's not too bad to get a pretty fast plot, but we would want to decide on what's a good increment. Let me make this a little bit more manageable. I wouldn't want to go by pi over 6, 30 degrees, because that's going to be a lot of values that we're plotting in. We don't want to work that hard. Let's go by pi over 4, 45 degrees. That will make it a little bit more manageable. So we're plotting sine x. So this will be the input. Think of that x now as where theta would have gone. These are the outputs y. And to start, we need to plug in 0. We now need to know what is sine of 0. Well, that turns into 0 right here. So that's our first point on the graph. And on the left, let's put it maybe here on the margin. Just going to scoot the participants window just a touch. Sorry, folks. We know that sine of 0 equals 0. The input here was the 0, and the output also here is the 0 that we got there. Now we're going to bump it up. Sine pi over 4. Anyone recall the value on that sign?
Square root of 2 over 2.
Absolutely. Thanks, Orlando. So this is root 2 over 2. And we've said before in the past, that's about 0.7. Let's put a positive 1 here, a negative 1 here to help us with the scale. So root 2 over 2 would be in this location, about 0.7. So here's the input, pi over 4, that we have on the x-axis. Output root 2 over 2 is on the y-axis. And that's our next point on the graph. So since we're going by pi over 4s, we'll just add pi over 4 to here. Pi over 4 plus pi over 4 is sine pi over 2. Any volunteers for this output? Good call. This one is exactly 1. And the graph looks like it should be, right? It's increasing. Looks like it should increase to a height of 1 on the next step. Turns out that's absolutely correct. We can plug a 1 here. The next increment takes us to pi over 2. And there's the output. Now, sine is a bounded curve, so at this stage, it has to start descending. It's a decreasing function beyond here. But the next input is sine 3 pi over 4. This one is still positive root 2 over 2. So a positive root 2 over 2, let's put first, here's 3 pi over 4. Positive root 2 over 2 takes us back to this height. And so that's our next location. All these values are now just repeating, and if it repeats, we're expecting a 0 right here. Let's write it out on the right. It would be sine 3 pi over 4 plus pi over 4 is just sine pi. And yes, that's right, sine pi is 0. So that's our next value. At pi, we take a value of 0 right here. Now, from here on out, we're going to obtain negative values for sine. We're going to start seeing, say, for this next tick mark, this is at 5 pi over 4. Sine at 5 pi over 4. We know it involves a root 2 over 2 because the reference angle is pi over 4. But we also know that this terminates in quadrant 3. Sine is negative there. So we throw a negative on that when we were in chapter 5. Back over on the graph, that just means we're down here on the negative end. Let's plug in negative root 2 over 2 here for the scale. And that's our next value here. Keep in mind, this is a by hand sketch. I'm trying to get these increments exactly right. They'll fluctuate a little bit, making the curve look a little bit weird, but that's okay. I wouldn't take off points on your homework sets either. Your curves don't have to be perfect. They just have to be okay. I will define what okay means as we go to solve these. So after 5 pi over 4, let's see, where are we? We're at 3 pi over 2. We need a volunteer. How about someone in Zoom? What is sine at 3 pi over 2 evaluate as?
-1.
Good call. The pi over 2 is a reference angle. So we're expecting a 1, but it's negative because we're not on a quadrant. We're on the lower end of the y-axis. So good call. That means at -1, 3 pi over 2, we'll put down a value right about here. This gets a little bit tricky because I'm kind of far away from my scale, but we'll do the best we can. After 3 pi over 2 is 7 pi over 4. And these are starting to get redundant, but they should. These are periodic, so we should see redundancies. Sine 7 pi over 4 is just back to a negative root 2 over 2. So we hit a minimum value here. Beyond 3 pi over 2, the curve is just increasing. So we're increasing to this height. And add pi over 4 to that, it's 8 pi over 4, taking us to 2 pi. But we did that already. 2 pi terminates in the same location as 0 does. Let's write it in just for emphasis. Sine at 2 pi comes out as 0. So now the curve is climbing up, hitting 0 right here. So that's one period of our sine wave. The tricky part is actually plotting it. What we shouldn't do is this. You can never cut yourself on a sine wave. It's not a saw blade type of wave. Try to curve it a little bit to make it look about like this. It takes some practice. I'm not very good at it, so my sketches sometimes look a little weird. But even if they look even worse than this, as long as you're going through the points, there's no sharp peak right here. That's excluded for sine curves. You're going to be in good shape. This is what a sine wave looks like. Well, we can now say the period. We'll often just say P for period is 2 pi. And we now know this because if we calculate beyond 2 pi, well, it'll go up to root 2 over 2, up to a positive 1. The whole thing is just cycling in the same exact way that we saw here. The next thing is we want its amplitude. Any volunteers for what the amplitude should be on the sine wave? Good call.
It's 1.
It's the distance. Sorry, say again, Hayes.
It's 1.
Yeah, good call. Good call, Michael and Hayes. It's going to be a height 1. You just go to the midline. The midline on this is the x-axis. Measure from here to here, and it's a 1. So amplitude is 1 on this thing. Let's see. We also want domain and range. Those things will be important down the line. The domain of sine and cosine are both the same. You can say it in a couple ways. You can just write out all real numbers. You could use this symbol. That symbol is the chalkboard bold symbol for all real numbers. Or you could write out this way. If you're a fan of interval notation, the domain of sine is from negative infinity to positive infinity. Next thing we want is range. Range is somewhat conflated with the amplitude, but it's not quite the right thought. The range is the extent from the minimum to maximum of all the y values that were obtained. So our range on this, I would specify this in interval notation. A bracket says you do obtain a minimum of -1. A bracket here says you do obtain a maximum value of +1 as well. So these are the pertinent facts for y equals sine x. What we would like to do is the same exact thing for cosine, but the punchline is all of that information is the same for cosine. The only thing that does change is the wave. Cosine starts at a +1 when you input a 0. So we don't have enough time to do the whole cosine wave, but this is about how it would look. Or roughly, I've got to get that just right. Something more along these lines. If we plot the cosine wave, that's what it would look like. Well, that's in
Is
fact,
that the one you write for domain? Is that like it means real numbers? Or like that
this
one?
right here. Yes.
Mhm.
That's designating all real numbers.
Okay,
I know it's a pretty common symbol, so let's put this in the notes. That symbol means all real numbers. It shows up more and more and more the more math we take. In a calculus course, it becomes pretty common and that kind of stuff. Other questions at the moment? Okay, well, we made some pretty good headway into these notes. When we come back after the weekend, we're going to plot cosine, and then we're going to see how do we plot all the transformations of sine and cosine. The sine wave is nice because you can adapt this by changing the period, changing the amplitude, changing the midline to real world data that you suspect is periodic as well. So that's the purpose of this stuff right here. We want to be able to plot these functions for the purpose of modeling real world data. But I think this is a good stopping point for us. We've transitioned from the unit circle to plotting y equals sine x on an xy plane. I think that's a good amount of work to absorb over the weekend, so this will be our stopping point for today. Any other last questions, folks, before we call it a weekend and wrap it up?
So with amplitude, is it always going to be positive then?
Yes, that's a good concept with amplitude. It turns out the formula for calculating amplitude involves an absolute value, so it's always a non-negative value. We'll always report something positive for amplitude. Other questions at the moment?
do we have any homework due next Tuesday?
Let's take a look at that. So for next Tuesday, it looks like this one was due today, but we did have a mention on the extensions here. If you need extra time, that's totally okay. This one is set to be due on Tuesday, February 20th. Looks like we're all set next Tuesday. Other
Okay.
questions so far? Okay, well, have a great night, folks. If you have any other questions, I'll be happy to help out. But I think this will be a good stopping point for us. We'll continue on this when we come back on Tuesday, and probably next week we'll make work into section 6.2 as well. Yep, you betcha. Thanks, folks. Steve. No worries about that. It happens. And here's yours. You bet.